human newborn typically takes around 2 to 3 months to recognize their primary caregivers, developing the ability to differentiate familiar faces from unfamiliar ones. Initially, their vision may be blurry and unfocused, yet they still begin to understand a measurable amount of the world around them. However, with the sudden advent and surge of artificial intelligence tools that utilize deep learning networks, the learning rate of an infant is, quite frankly, no competition at all. In recent years, we've witnessed remarkable progress in deep learning. Recent technological advances have made it possible to create powerful systems like neural networks, which mimic the human brain, in a very short period of time. This led me to ponder, how long does it actually take to train a neural network? According to various sources, including Google, training times can vary from just a few minutes to several weeks, depending on factors such as hyperparameter tuning and the quality of the data being fed into the system. This curiosity became the foundation for my experiment, which focused on the use of deep learning to locate cancer, specifically lung cancer. Lung cancer is a major health concern, responsible for the deaths of nearly 1.8 million people worldwide each year. In Canada alone, an estimated 20,600 Canadians will perish from lung cancer this year, a number that is projected to rise if proactive measures are not taken. Lung cancer is particularly deadly because it originates in one of the body's most vital organs, the lungs. For the specific task of detecting lung cancer, convolutional neural networks, or CNNs for short, are considered the gold standard in image classification. CNNs are adept at processing visual data, making them ideal for analyzing medical images. They work by interpreting data and transforming it into various outputs, such as classification and segmentation. The application of CNNs in medical imaging has gained traction over the past decade, demonstrating their potential in cancer diagnosis. In fact, CNNs have shown such proficiency in identifying cancerous cells that they can outperform human radiologists. For example, GoogleNet, introduced in 2012, achieved an impressive AI detection accuracy of 89%, while human pathologists average around 70%. The essence of my project was to develop a CNN named OncoAI aimed at identifying the presence of cancerous lesions in lung scans within the limited span of a week, testing the abilities of CNNs in a short window of time. My ultimate goal was to help narrow the divide between the availability of resources that could potentially save lives. But how does a CNN actually work? To illustrate, what do you currently see on your screen? If you have decent vision, maybe you might assess the image in front of you as possessing qualities that point towards it being a cat. And this other picture seems to be a dog. Oh look, another one with a house. You are viewing these photos from the confines of a flat 2D screen, be it a phone or computer, and your eyes capture light, which is then processed by the retinas and converted into electrical signals that the brain interprets. Initially, these signals do not convey recognizable images. Instead, they represent basic light waves. As the signals travel through various layers of the visual system, they form a comprehensive picture that we can understand. In contrast, CNNs interpret images as binary data, composed of ones and zeros. Each pixel carries a numerical value, and images are represented as matrices of numbers. The operation of CNNs involves identifying features at multiple different levels. Low-level features capture edges, textures, and small patterns. Mid-level features detect structures such as lung contours and airways, while high-level features recognize complex patterns like the presence of tumors. This hierarchical feature extraction is achieved through convolution, where learnable filters move across the image to detect salient patterns. After convolution, max pooling is applied to reduce dimensionality by selecting the maximum value in each patch, thereby retaining the most significant information while reducing computational complexity. This helps preserve important spatial features and improves model efficiency. In my experiment, there are important factors that are essential to the effectiveness of the project and the performance of my CNN. My responding variable is the accuracy, which is the outcome and precision of the CNN, such as whether or not it can accurately predict the presence of cancer in the CT scans. My manipulated variables are the CT scans, which are of varying type, and hyperparameters, which include the learning rate, batch size, epochs, number of layers, model architecture, regularization, and data augmentation, which will all be tuned in various ways to give the model the necessary resources to flourish. My controlled variables are the number of images, which will continue to remain static so as to remain at a constant rate of image exposure, programs used, which are the softwares of VS Code, Windows Notepad, GitHub, and overall Python, and the time frame, which encompasses the basis of the project to assess the potencies of CNNs in a defined length of time. The procedure was systematic. I created scripts for my code, set up a GitHub repository to track progress, and selected datasets from Kaggle that included both cancerous and non-cancerous CT scans. To run my script without relying on a command line, I deployed the application after ensuring all necessary dependencies were installed. After compiling the model, I trained it on the selected data. Throughout the training process, I recorded the model's accuracy and loss, as well as validation metrics. Every 2 days, I changed the dataset among 4 different options to improve generalization and performance. Through my experimentation, I achieved an accuracy score of 80% with OncoAI, showcasing the capabilities of CNNs in this context. I explored various architectures, including MobileNet v3, DenseNet 121, and EfficientNet BO, with EfficientNet BO yielding the best results as it was a lightweight model that worked well with the Streamlit application. Initially, the model performed strongly, but as the datasets evolved, I researched strategies to enhance model performance, including the use of Atom as my optimizer and the implementation of transfer learning. Debugging was a significant aspect of the project. The code required constant refinement to ensure smooth operation. For instance, I encountered issues with the GradCam predictions, and the model faced challenges with ambiguous CT scans that could belong to either class. Resource limitations, such as memory and storage constraints, restricted the use of more advanced models, but I still found success with EfficientNet BO. Ultimately, my findings highlight the immense potential of CNNs like OncoAI in improving lung cancer detection. However, ethical considerations regarding AI's role in healthcare remain crucial. While these technologies show promise, it is essential that human expertise continues to guide medical decision-making. In conclusion, my research illustrates the transformative potential of deep learning in cancer detection, aiming to enhance patient outcomes and inspire further exploration in this field. As we continue to advance AI technologies, we move closer to effective solutions that can significantly impact healthcare and improve lives globally. The journey toward integrating AI in medical contexts is ongoing, and I hope my work encourages others to delve into the exciting world of deep neural networks, particularly in the fight against cancer. Another important step that I'm hoping to take is to partner with one of you guys watching to create an app interface to platform CNNs like this, to share with others to use, including health professionals and regular folk. So if you think you might be interested in that, please let me know down below. Anyways, thank you so much for watching this video. If you appreciate content like this, feel free to like and subscribe, as well as leaving your questions and concerns down in the comments below. Have a wonderful